there, welcome back to trigonometry. Today we are going to look at something very important. It's going to be used throughout the rest of the course, and it's called the unit circle. We're going to look at where it comes from and then talk a little bit about how you're going to use it. Now the unit circle, if you've never heard of it before, it's okay. The concept of it, you've heard everything that you're going to see. It's just the unit circle puts it all together in a really nice way. In this course so far, we've already talked about the trig ratios, like sine, cosine, tangent, secant, cosecant, cotangent. We even talked about the trig ratios when looking at things in terms of ordered pairs, x comma y. Like if you have some point x comma y, you can plot it on the xy grid, and you can look at making a triangle with one of the sides being on the positive x-axis here, or on the x-axis, positive, negative, doesn't matter. And then there's the hypotenuse of this triangle is going to be the radius, or this length here, from the origin up to the point xy. And then you can drop a perpendicular from the point xy down to nearest point on the x-axis. And that makes a little right triangle. And what we learned was that you could take that right triangle and you could look at it and go, well, this side here is x units long, this side here is y units long. And then we called, this side r for radius, because that length is like the radius. So if it's situated in a circle, that length is the radius of the circle. And we learned that we could say, well, sine of theta is not only opposite over hypotenuse, but we could say y over r. We could say cosine of theta is not only adjacent over hypotenuse, but x over r. And we could say that tangent of theta is opposite over adjacent, or y over x. And then you've got your reciprocal identities too. Cosecant of theta was r over y. Secant of theta was r over x. And cotangent of theta was x over y. Now with the unit circle, what's going to happen is you're going to look at these points not at just of xy being anywhere, but rather xy being on a circle that has specifically a radius of 1. So we're going to assign r to equal 1, and that's going to give us a unit circle. So we'll have a point right here on the unit circle of 1, 0. Of course, origin is 0, 0. And with r being 1 on the unit circle, sine of theta is not just y over r, but y over 1, or y. Cosine of theta is x over r, or x over 1, which becomes x. Tangent of theta is still y over x. Cosecant will be 1 over y. Secant will be 1 over x. And the cotangent will still be x over y. So if we specify that the circle that this point xy falls on is a circle with radius of 1, we're now looking at a unit circle. The unit circle is a circle with center at the origin and radius 1. And defining it with a radius of 1 becomes very convenient, because now you pick any point on this circle, any xy, the sine of the theta, like if you start from positive x-axis and go over to whatever that theta is, the sine of that theta will just be the y-coordinate. The cosine of that theta will just be that x-coordinate. The tangent of that theta will be that y over that x. So you get all kinds of neat things you can do with this. Now what we're going to do is we're going to take this unit circle and we're going to apply all the common angles. Okay, we're going to, 0 degrees or 0 radians. We're going to lay that out. Look at what xy is on that point. 30 degrees or 30 pi over 180, pi over 6 radians. Look at what that looks like. 60 degrees, 60, I forgot the 45 also, 45 degrees. That was the pi over 4. 60 degrees, that was the pi over 3. 90 degrees, that's pi over 2, and so on. And we're going to take this circle and we're going to lay out all of those common angles, but not just in the quadrant 1, but we'll also come over to quadrant 2 and lay those out there as well. And in quadrant 3 and in quadrant 4. And for each of those angles, there's on the terminal side of the angle, there's a ordered pair that falls on this circle here. And whatever that ordered pair is, that can tell you a lot about what the sine of the angle, cosine of the angle, tangent of the angle, and so forth. Okay, so you might be wondering, well, what's the ordered pair? Well, the really neat thing about this is that with the r being 1, there is an intense relationship between the theta, the central angle, and the arc measure. Okay, we previously learned that s equals r theta, right? Your arc length equals the radius times that angle measure, and we're talking in radians. So remember, we're going to be in radians here. But in this case, if r is 1, if your radius is 1, s equals theta. The angle in radians is the same as the arc length in radians. It's the same number, same measure. And with that fact, we can start talking about the trig functions as circular functions. When we're looking on the circle and when we're doing everything in terms of the arc length. So when written as functions of arc length x. Arc length s, which is a real number. So instead of talking about theta, we can talk about arc length. Well, if arc length and theta are the same, then whatever the sine, cosine, and tangent are for theta, it's going to be the sine, cosine, tangent, etc. for arc length. So sine of theta equaling y, we can instead say sine of s equals y, sine of the arc length. Instead of cosine theta equals x, we can say cosine of the arc length is x. Instead of tangent of theta being y over x, we can say tangent of the arc length is y over x. So we apply that here. We can not only talk about with thetas, we can talk about it with arc lengths, but then we can start putting on all these common angles, and we can say, okay, we know what the sine, cosine, and tangent are for 30 degrees, or sine, cosine, tangent are for pi over 6 radians. We know those. We've developed those common ratios before. So whatever they are, they're going to be the same on the unit circle. And so then it turns out too that if sine of theta is indeed y, and we know that what the sine of 30 is, then we know what the y coordinate is of the point on the circle. Little things like that. Okay, let me draw a picture. It'll be easier to see it if I draw a picture. Alright. We've got our circle. Forgive me for not being perfect with this. I know these axes don't exactly intersect at the center of the circle. I'm just kind of doing a quick sketch so you can see. But let's draw it in blue just to give a different color. Alright, so let's say we've got our theta here. This is the unit circle, so that's 1, 0. So this theta here, that's the same as this arc length s. But let's let theta be 30 degrees, which is the same thing as pi over 6 radians. Well, we know the sine of pi over 6, cosine of pi over 6, tangent of pi over 6. We know all of those values. We know that the sine of pi over 6 is going to be 1/2. We know the cosine of pi over 6 is square root of 3 over 2. We know that the tangent is square root of 3 over 3. We know that from previous work with right triangles. You know, if we think about this as a right triangle. But now with circular functions, if that's true for theta, it's also true about the arc length. We now know that sine of theta is the same as y, or the sine of the arc is the same as y. So this point right here, the y value is going to be the 1/2. Cosine theta is x, cosine of s is x. If cosine of pi over 6 is square root of 3 over 2, then the x coordinate here is square root of 3 over 2. And we can go around and do this for all of those common angles all the way around the circle. But if you remember, the whole A Smart Trig class, in quadrant 1, x and y are both going to be positive. In quadrant 2, sine is positive. Everything else is negative. So that means the x coordinate is going to be negative, y coordinate is positive. And if you think about it, it makes sense. Because you have the negative x-axis, you have the positive y-axis. In quadrant 3, tangent's positive, which means they both have to have the same sign. The sign, x and y have to have the same sign. In this case, and then everything else is negative, sine and cosine. So we got negative, negative. You know, cosine's negative, sine's negative. But that, if you look at it, x-axis is negative, y-axis is negative. Then in quadrant 4, x-axis is positive, y-axis is negative. And if you look at it, in quadrant 4, cosine is positive. Cosine equals x. Everything else is negative. Sine is y. Sine is negative. Y is negative. So you'll be able to go around and not just do 30, 45, and 60, but then start adding these angles in too. So your reference angles work out the same as having reference arcs. Okay, let me show you a completed circle. Okay, it's kind of hard for me to squeeze all this into the screen here, but starting at the top half, right here you got 0 degrees. The point on the circle here is at 1, 0. So then at 0 degrees, you know that that's not only the angle measure, theta measure, but it's also the arc length. But you know then that the sine of 0 degrees, or the sine of 0 radians, is going to be 0 because of this y value here. You know that the cosine of 0 is going to be 1 because of that x value there. And you can go around, all the way around the circle, and you can look and say, okay, at a glance I can see, all right, let's go over here to 120. 120 degrees, that's this theta here, or the arc length, if you put it in radians, 2 pi over 3. And for arc length, you have to have it in radians. So you got 2 pi over 3 radians for the arc length. But remember the whole thing about reference triangles? You can also think about it with reference arcs along here. Dealing with radians. Well, if going all the way across is pi radians, we're interested in this reference arc here, this reference angle or reference arc. Pi minus the 2 over 3 gives us pi over 3 for that reference there. Well, pi over 3 has coordinates 1/2 comma square root of 3 over 2. So you see those coordinates here, but since we're in quadrant 2, sine is positive, cosine is negative. Or if you look at the axis, this is the negative x-axis versus the positive y-axis. So x is negative, y is positive. But that also translates into cosine and sine. And you can do that in any quadrant. Like if you look down, let's say you go all the way around to here. Notice I'm going counterclockwise, I'm going positive direction, but you can also do negative angles. The theta is 4 pi over 3, also known as 240 degrees. But the reference theta in here, you subtract, or you take 180, or in this case pi, and you figure out, well, how much more gets you to 4 pi over 3? Well, you subtract the 4 pi over 3 and the pi, you get pi over 3. Okay, we know pi over 3 to be 1/2 comma square root of 3 over 2. So we see the 1/2 and we see the square root of 3 over 2, but in this case we're in the quadrant 3, so it's negative x, negative y, negative, negative. So our cosine of 4 pi over 3 is negative 1/2. Our sine of 4 pi over 3 is negative square root of 3 over 2. And then to do the tangent, just put y over x and simplify. So the tangent in that case, put those over, the 2's will cancel, you end up with positive square root of 3. So all kinds of fun stuff with the unit circle. Now you're not going to be allowed to use the unit circle, like you're not allowed to take a copy in for a test or for the final. So you are going to basically want to memorize this so you can have it at your fingertips when you're doing your problems on your test. But keep in mind you don't have to sit there necessarily and memorize the numbers and spit them back out from rote memory. Keep in mind this all comes from the right triangle stuff we learned. 30 degrees here, you can think about that as that right triangle having a 30-degree angle here. And figure out what your sine and cosine are. Remember, the cosine's the x, sine's the y. 45 degrees, same thing. Think about the reference triangle. 60 degrees, think about the reference triangle. Even over here, you can think about the reference triangles. And it'll translate from trig functions to circular functions because the thetas end up having the same value as the arc length. So you can use the reference triangles to get your numbers and then know that it works for the circular functions. Okay, if we look at this a little more closely, we can make a few interesting discoveries here about our domains of the circular functions. If you first look at sine, talking about domain. Notice on the circle that you know that sine is going to give you the it's in the y values. If you notice the y values in your circle, they go from 0 up to +1 or 0 down to -1. They don't go any further than any lower than -1. They don't go any higher than +1 here. Also, they end up including all values in between -1 and 1 because this is a smooth, continuous circle. Even though there's only certain angles marked out, you can all the angles, all possible angles can be represented on here. Everything in between 0 and 30 and 45 and 60 and stuff can be represented on here too. So your sine ends up looking at using all possible values of y from -1 to 1. Oops. When you get your answers. Sorry, let me scoot this over. Let me rewrite this. We've discussed the range before. But with the domain, if you think about how you got the -1 to 1, you've got this smooth, continuous circle. See that? And so you end up being able to represent any angle on here. Anything from 0 to 360. And then you could keep going. You can keep going around and around. Or you can also go the opposite direction. Go negative direction and do negative angles. So the domain, you can take the sine of any real number. But then the answer is always going to fall somewhere from -1 to 1. And it can include -1 and 1. If you look at those ordered pairs. Cosine, you can do a similar study. Cosine's all the x values. You can go around the circle counterclockwise as many times as you want. You can go clockwise as many times as you want. You can always use these reference angles to help you, or reference arcs to help you find your cosine values. So your domain is -∞ to infinity. But your range, looking at your x's, you got a 1 here, a -1 there, and then you can include everything in between. So the range is also -1 to 1. So domain here, think about that as the input, like what angles you're finding the sine or cosine of. And then the range, that's the output. That's whatever values you see on these ordered pair, these points on the circle. Tangent gets a little trickier with domain. Tangent, the range ends up being -∞ to infinity. Because you're able to do all kinds of ratios along here. But you might notice when you get to certain places, you're not able to do, you're not going to get some good results. Like if you look right here, tangent of pi over 2 is y over x, right? Well, in this case, y is 1, x is 0. We get something that's undefined. Now, when we go to graph these later in future lessons, you're going to find that at those values, you're going to have something called a vertical asymptote. It's an invisible vertical line that the graph never crosses or touches. And it can't, because at those values, the tangent ends up being undefined. So when you're looking at your domain, at pi over 2, or at any version of pi over 2, if you go around 2 pi times, you can go around 2 pi lots and lots of times, or you can you either go positive direction or negative direction. And either way, every time you go around 2 pi times, you end up back here, your tangent's going to be undefined. That also happens down here at 3 pi over 2. Because look there, y over x, you got negative 1 over 0, which is undefined. So at 3 pi over 2, that also happens. And if you go around 2 pi times, you end up back at 3 pi over 2. If you go around another 2 pi times, or if you go the other direction, negative 2 pi times, go around another negative 2 pi times, you end up back at 3 pi over 2, and you end up with the tangent being undefined. So the domain there can be arc length S such that S is not equal to 2n plus 1 times pi over 2. Okay. 2n plus 1. Well, if n is 0, that's 1 times pi over 2 is pi over 2. If n is 1, 2 plus 1 is 3. 3 pi over 2, that handles this situation. 2 times 2 is 4, plus 1 is 5 pi over 2. Well, that takes pi over 2 and adds 2 pi to it. Or you can go the other direction if n is negative. So n is an element of the integers. Z stands for integers. So there's your domain there. Now it turns out that the secant function is going to have the same. Because if you think about secant is 1 over cosine. So anytime your cosine ends up being 0, secant is 1 over 0 or undefined. Cosine is 0 at pi over 2 and at 3 pi over 2. So it ends up having the same domain. Cotangent and cosecant, little different story for domain. In the case of cotangent, that's x over y. So in that one, you're looking at where y is 0. Things are going to be undefined. So that one, you've got this point here and this point here. 0 and pi. Well, if you go from 0 and add or subtract 2 pi, you'll end up back here. Or if you go from pi and add or subtract 2 pi, you'll go back here. So that ends up giving you any n pi. S cannot be, it's any s except s's that equal n pi. N is an integer. N is 0, you got 0 pi, that's right here. N is 1, 1 pi, that's right here. N is 2, 2 pi, that's right here. N is 3, 3 pi, that's right here. And that ends up always coming to bounce into one of these points. If you do negative 1 pi, it's going to take you this direction, but you're going to land here. Negative 2 pi, keep going that clockwise direction, you're going to land here. So any integer times pi, and the domain has to exclude those values. It's going to end up being undefined for cotangent and cosecant. But keep that all in mind as you're working on problems. And that's really going to be something that stands out when we start graphing. Because not only does tangent have vertical asymptotes, but secant, cotangent, cosecant will also have vertical asymptotes. Ends up being rather interesting. The graphs end up being very interesting to watch and look at. Okay. Well, that basically introduces to you the unit circle. I've made a mess of these on here. If you look closely under your content section of your PAL, you'll see a unit circle file. Actually, there's actually two of them. One of them I like better because it has more things marked on it. You can always print those out or download them, whatever, and use them for your studies, but you won't be able to bring them in for a test or the final. So you'll want to be familiar with the unit circle in your head. But when you're working problems, nothing wrong when you're doing your homework with having the unit circle right there to refer to, as long as you know where everything came from, and as long as you know how to use it. So know about the x and y, what they stand for, cosine and sine, and so forth, and know how to get these cosines and sines and tangents, etc., of these common thetas. Okay. So one more little thing. Let's see here. Let's just do a couple quick little practice of finding values using the unit circle. Let's say you want to find the exact value of sine of negative 3 pi. So you're asked to do something like that. Well, thanks to the unit circle, you can say, well, I'll start at the 0 degrees. Negative 3 pi means I'm going clockwise direction. If I go around halfway, that's pi, negative pi. Another halfway will give me to negative 2 pi. Another halfway gets me to negative 3 pi. So I land here. And I'm being asked to find the sine. So all I got to do is look at the ordered pair. The y value is your sine value, and that's 0. So the sine here equals 0. Okay. Let's say they ask you to find, let's say they tell you that, let's see here. Let's say that they tell you the tangent of s is negative square root of 3 over 3. But they also tell you that s is in the interval from 3 pi over 2 to 2 pi. Okay, so that's not sine, that's s, the arc length, is in that interval. Well, 3 pi over 2 to 2 pi, that's this quadrant 4 right here. And they're telling us the tangent of some arc is negative square root of 3 over 3. So if we look in that quadrant, and we look closely, remember tangent is y over x. Tangent is found by doing y over x. Well, if you have to have a negative square root of 3 on top, I'm going to look at y, and I'm going to look at this one more closely. If I put negative square root of 3 over 2 on top, if I put 1/2 on the bottom, doesn't look like that's going to reduce very well, right? Because the 2 is reduced, but then you're going to be left with negative square root of 3, and that's not what I got. So, let me look at this one. If I have negative 1/2 on top, square root of 3 over 2 on the bottom, 2 is reduced, I got negative 1 over square root of 3. Got to rationalize the denominator. You end up with negative square root of 3 over 3. Woohoo! So right there, that ordered pair works for the tangent to make this tangent equal this. So then I need to focus on the number there. So s, in this case, must be 11 pi over 6. So 11 pi over 6, I was basically doing an inverse tangent. I was, s here was the inverse tangent of negative square root of 3 over 3. But I was able to use the unit circle and say, well, let me find the ordered pair that gives me the negative square root of 3 over 3 for tangent, and then see what the theta is in radians. So you can work both ways with the unit circle. You can either find the tangent of an angle, sine, cosine, tangent of an angle, or you can do inverses on here too, because you have the x's and y's laid out for you. The sines and cosines laid out. Then real quick, just wanted to do a couple quick calculator things with you, and then we'll wrap up the unit circle lesson here. If they ask you to find, let's say they ask you to find the sine of 3.42, and they don't say degrees. They just say find the sine of 3.42. Well, if they don't say degrees, that means this is in radians. So it's very important to go to your mode and go down and select radian if it's not already selected before you try to find your answer. Because if you don't select radian, you will get something that you don't realize is wrong, because it might spit back some answer, and if it's some crazy decimal, it's like, oh, that might be right. So it's imperative, double check your calculator. If you're dealing with degrees, make sure you're in degree mode. If you're dealing with radians, make sure you're in your radian mode. And the way you can tell which one, degrees will have the little degree symbol, radians may not have anything. It might say radians, but more than likely it just will have nothing, no symbol. And then so you got to double check your calculator. If they are asking you to find something like cosecant of negative 2.7335, well, cosecant's really 1 divided by the sine, negative 2.7335, and then you're able to get your numbers from there. Okay, but just remember to be in radian mode. That's the really important thing there. All right. Well, stay tuned. I still need to continue using what we've learned here with radians and the unit circle and so forth. But we're going to get into some practical applications such as linear and angular speed. But I'm going to save that for another recording. So please do join us for the follow-up to the unit circle introduction. Thank you.